Good afternoon and welcome to the Open Systems Media Automotive Technologies Virtual Conference. My name is Rich Nass and I will be your moderator for this event today. I am also the Executive Vice President of Open Systems Media. I lead the embedded and IoT teams for embedded computing design. The Automotive Technologies Virtual Conference is made possible because of our sponsors, and that would be Texas Instruments, IAR Systems, AD-Link Technologies, Imagination Technologies, and Corvo. This may or may not be the first session you're attending at the conference today. A little while ago, we heard a great presentation from Sean Prestridge of IAR Systems, and he spoke about the ISO 26262 certification process. That presentation is now available in an on-demand version. And then later this afternoon at 4 o'clock Eastern time, we'll be hearing a presentation from Corvo, where we will be discussing the V2X spectrum coexistence challenges that are presented by autonomous vehicles. And in between all those presentations, there are a slew of pre-recorded sessions, about 15 of those, and you're welcome to view those at your leisure. They are covering ADAS, autonomous drive, electric vehicles and powertrain, in-vehicle infotainment, and safety and security. Okay, so back to the topic at hand, where we will be looking at the latest techniques in battery management systems for the automobile. Our presenter here is Daniel Torres of Texas Instruments. I won't read his bio because you can see it up on the screen there, so just take a look, but you'll see that Daniel is more than capable of discussing this subject. I would classify him as an expert. Before Daniel starts, let me go through some of the housekeeping items. His presentation will take about 40-ish, 45 minutes. And then when he's done, we'll answer your questions, and we will answer as many as we have time for. You'll see on the console window an area where you can enter your questions in real time. And as I said, we will address as many as we have time for when Daniel's done. If we don't have time to answer your question as part of this presentation, somebody from Texas Instruments will respond to you after the session is over. So everything gets answered. It just might not be as part of this live presentation. If you have an issue with the operation of the presentation, like if the slides don't advance properly or my audio doesn't sound as you would expect, just put that question into the question box and one of the technicians will get back to you with a fix. There's a maximize button that allows you to see the slides in a larger window. And when we're done, this will be available in an archive version. So if you want to review it later, or if you want to send it to a friend or a colleague, it'll be there for you. Okay, enough from me. Let's hear from Daniel. All yours, Daniel. Take it away.
Thank you, Rick. I appreciate it for the time, everyone. Let's jump into it. So let me share with you guys how wireless BMS fits into the overall TI scheme of things and where we've been working on in the automotive industry. As you can see on these slides that we have 4 buckets where TI has been providing solutions to the automotive industry. So really where wireless BMS fits in is around the hybrid and electric vehicles, basically working on providing solutions for the electrification efforts of the powertrain and while helping to reduce emissions, right? So that's where we are fitting in, along with providing industrial solutions for the smart grid and providing enough energy for that. One of the things that we really focus on is how do we make solutions that help us out to create a better world. So this is one of those things that we believe has a great sense of purpose, providing best-in-class solutions that help us out to create a safer world and a cleaner world. So that's why when we came across this problem with our customers, we got really excited about how we can actually help them out to achieve their goals about creating a vehicle that can expand the mileage, the range, while reducing the overall system cost. The journey in electrification, as we see it, is, how do we get down to a zero-emission transportation, right? Because we all know we have different types of vehicles now starting this journey with micro hybrids, 12-volt systems, right? And then finally getting at the end of the, evolution with fully battery electric vehicles, right? Where customers and systems integrators, OEMs are designing systems for high voltage, going beyond 50 kilowatts. That's how the industry has progressed and how TI has been helping customers to achieve these goals. Moving on to how the battery management systems look like today and how they will look like tomorrow, you can see that today the most widely adopted architecture when it comes down to the interconnects of the different battery packs and battery modules is run wide. It's a solution that has been working so far for smaller designs. When it comes back to basically design systems that need to scale up and customers that want to really reduce time to market, this becomes a more cumbersome and challenging solution because you'll have to think about the layout of the batteries, the layout of the packs, and how you do the interconnect. So you have to design that from the get-go. And what we've seen in the industry happening now is a strong desire to have a more scalable modular platform that allows OEMs and system integrators to basically decide a platform that can mix and match different battery modules and arrays, maximize the space of a given chassis, and then we use that BMS platform across different product lines, different car lines, whether if it's a small sedan, but all the way to a big truck, right? All of these systems have different needs and capacities, but at the same time, the fundamental core of the technologies are the same. And so that's why we believe having a wireless technology helps customers to basically scale up and down in their needs for having different types of BMS architectures. So let's zoom in into what a wire battery management system looks like. So as you can see on the top side of the corner, you see that there are some battery packs and battery arrays. We have a cell monitor and balancer, our BQ79616. So that's basically monitoring the voltage at the cells, the temperature. It's also providing a very strong, robust, secure communication interface via daisy chain through the rest of the pack and report that information back to the main control unit, which is sitting on your bottom left corner. So this is how a typical system looks like. You have low voltage wires running around for interconnecting all these different modules and being able to acquire the voltage, the temperature, the current signals, and some of the things that customers want to measure, right? From a kind of a block diagram point of view, this is how the system looks like. So you have your cells arrays. You have multiple cell supervision units with the BQ79616, our 16-channel cell monitor and balancer. This is showing a daisy chain communication with capacitive isolation, as you can see here. You can have arrays of 12, 16, 14 channels, depending on the size of the module, and even beyond that. And interconnect all these things, as I mentioned, through a daisy chain configuration to the main control unit. In this case, we call it battery control unit. In that unit, you have a safety MCU, you have a contactor driver, you have some other signals that you want to acquire coming from what we call the battery junction box or the battery disconnect box. And as you can see, there's a huge set of interconnections happening between the battery junction box and the battery control unit, right? You have a high voltage connector, basically providing the pack voltage, the link voltage, also the charger voltage, right, of those terminals across the relays of the electronic switches. And then those signals are basically sensed in the battery control unit on the high voltage side and then isolated to be able to measure by the MCU. At the same time, you have, relatively speaking, low voltage signals for driving the contactors, also acquiring the temp sensor signals, and then also the current signals like Hall sensors or shunts. So this is a cumbersome way of architecting the system. It's how it's been done traditionally. So one of the biggest challenges, first of all, is how do you do all the interconnects across the different boards in the system? And typically, these boards don't sit in the same place, right? Physically speaking, in the chassis. So you're talking about probably a few inches, a few centimeters worth of connects, but it also poses challenges related to harnessing and cabling and the reliability of those interconnects and the complication on how to make sure that you don't create some challenges along those interconnections. So this is how it's happening now. We've seen a big need in the industry to go to a different kind of architecture. We'll talk about that in a minute. Now, let me quickly touch on what our cell monitor and balancer is, the BQ79616. It's an ACLD compliant capable device that is reporting the voltage, the temperature, information from the cells. It's able to sense up to 16 channels. It has a built-in protector for monitoring conditions on under voltage, over voltage, under temperature. It also has on-chip cell balancing capabilities using passive cell balancing. Best-in-class accuracy on plus minus 2 millivolts. And it's a very highly integrated device that also has a communication port to be able to interface to an MCU through UART, or to be able to interface to a complete system through the AC chain using plus minus 20 volt signals. This is a great part for very widely used and adopted by many customers right now. Going deeper into what the IP looks like on this device, so we have multiple signal paths for acquiring critical signals like voltage and temperature. So as you can see on this picture, we have a main ADC. It's a SAR ADC, so it's capable of quickly acquiring signals coming from the different cells. We also have a redundancy with the auxiliary ADC, as you can see right behind the main ADC. Then we have a cell balancer circuitry, as I mentioned. We have on-chip FETs, being able to do all the balancing, control through temperature or control to the CL interface command. With an on-chip FET that has around 2.5 ohms of resistance when the drain is on. We have additional GPIOs for customers to interface temperature sensors, or use it as an auxiliary input voltage, or use it as a SPI master, or just a generic GPIO. So it's a very flexible interface. And as I mentioned a few seconds ago, we have a fully independent hardware protector that is capable of sensing out of the same signal path as the main ADC, challenging conditions or happening in the cell, which is, under voltage conditions, over voltage conditions, over temperature, under temperature conditions as well, and report that information back to a main MCU through a fault line or through a CL interface. And then on the top corner, you can see that we have the vertical interface, communication interface for handling the UART interface, CL interface, or the DC chain signal. So that's how this part looks like internally, and the main blocks going along the BQ79616. What are the current challenges on with BMS in EVs? So we already touched a little bit on this. So mainly it's around how do you create a scalable, cost-effective platform that can be reused across different product lines and car lines, right? And so right now, one of the biggest pain points we've heard from automakers is related to warranty repairs due to cable failures, and how expensive that is, how it's difficult for the dealerships to be able to do this on site, and that they have to ship all these defective units, complete BMS unit to the factory. So that's a pain point. And so what they're looking at is how can they make the system more modular so they can allow the dealership starting to debug these defective body modules without having to ship the whole BMS, or without having to replace the whole BMS system, right? And so that's why there is a big push in the industry to find a solution for that. The other thing is, as I mentioned, right, the winding harnesses and connectors are the common source of cable failures, given the fact that these cars are on the road for miles and miles and miles. There's vibration. There is a potential for these harnesses to break or the cables to break and not being able to pass critical information back to the control unit. So having that in mind, there is a big push, as I said, in the industry to look for alternatives. And so what we are presenting as a solution, if you recall the first slide where I presented a typical picture of a wire system, now what we have is basically having two devices, one keeping the cell monitor and balancer with the BQ7616, and then attaching that device to a wireless SoC, a wireless MCU, in this case CC2662, to be able to create a radio link, an RF link, between the body modules and the body control unit. And so, basically removing those cables needed in the daisy chain to be able to pass temperature, voltage, and then over voltage, under voltage conditions, right, in a critical fashion. So from a block diagram, this is how the system looks like, right? So now instead of having a daisy chain communication happening between the cell array back to the body control unit, now you have basically different wireless nodes with the wireless chip attached to the body control, body monitor chip, right? And then passing that information back to the body control unit, which also has a network coordinator interconnected or connected to the main MCU through a CL interface. It could be UART, SPI, I2C. So again, nothing has changed on the junction box, and looking at how do you actually start to making the system more scalable and modular. Now, quickly introducing what the wireless SoC looks like. This is basically a wireless MCU with a Cortex-M4F core. That's the main application processor, the main MCU on the chip. It has a fully autonomous radio with a Cortex-M0, basically managing all the radio interfaces. It has ROM for saving some configurations on chip. And then it has programmable memory up to 352 KB of flash with 8 KB of cache, and then up to 80 KB of SRAM with parity check. And then it has a big suite of additional peripherals, generic GPIOs, serial interfaces, DMAs, in addition to a very interesting sensing control unit. We call it the sensor interface. It's basically a sensor controller managing ADCs, SPI interface, time to digital converters when the whole MCU is in low power mode. So these little engine can be on while the rest of the chip is actually in low power mode. As part of the key features, this device supports the TI wireless BMS protocol that we developed for this specific application. It's running on a 2.4 gigahertz band. It's a functionally safety quality managed part. What that means is that it's a quality managed part that will come with additional information to help our customers to do the decomposition analysis when it comes down to understanding how they can meet their functional safety goals. As I mentioned, it's an AEC Q100 qualified part. It's grade 2, goes from -40 to 105C. Very low power, best-in-class performance on the radio, specifically around the link budget that this little radio can provide. It goes from plus 5 dB on the TX power, and then a really great radio sensitivity of -97 dB, which gives you around 103, 105 dB of link budget. And that's really important for applications like a body management system where you are in situations where you don't have a line of sight, right, or where you have obstructions in some case. So you want to maximize the amount of energy that you can radiate and also the sensitivity of your radio to be able to pick up those weak signals. With that being said, let me go to how a wireless interface or wireless network will look like. So as I mentioned at the beginning of this call, we have the cell sensing unit. You have a body monitor chip attached to a wireless SoC, so the BQ79616 to CC2662. You have one per body monitor, and you scale up those modules as you go. So in this case, you can have modules of 16S array, 12S array, or 14S array, depending on the need. And then each of these modules has a unique ID and all the provisions needed to be able to report the information back to the body control unit. And so on the body control unit, as you can see, you have your main MCU, and then you have a wireless master, CC2662, basically coordinating all the network traffic and then passing all the critical information from all the different nodes that exist in the network back to the safety MCU. And then that safety MCU can interface to the rest of the ECUs, the computers in the car through CAN. Okay. Now, our network can support more than 100 nodes. It's a very scalable network configuration, so you can have, that means that you can have up to 100 modules like this. So what that means is that you can scale up and down in terms of the capacity of the BMS. So with the exact same modules, you just have different arrays in your layout for the BMS, and so you can have different chassis that can potentially leverage these platforms. So you can have chassis for a sedan with a smaller BMS capacity down to, I don't know, 50, 30 kilowatts per hour, and then all the way to trucks that may need hundreds of kilowatts per hour, right, 100 to 200, right? And so you can scale up and down depending on how many modules you want to have in your system. And so this configuration of this network topology can support up and down the number of modules that you need. It's capable of reporting the data every 100 milliseconds, which is the typical fault-tolerant time for meeting functional safety goals. And the reason why is because it's a really fast protocol that has been optimized for this use case. It's a concept that has been assessed by TÜV, and that's, that's one extra step that we took when we started this journey a few years back. We understood that functional safety is a key factor when it comes down to providing a complete solution to system integrators and car manufacturers. And so for that reason, we went ahead and wanted to certify our functional safety concept with TÜV. And so that gives peace of mind to our customers, provides freedom to develop reliable and system-level designs across different platforms. So the report on the assessment for this concept is available on TI.com. We'll share with you guys the links where you can actually request access to it. This is basically just showing the certification on, stating that we enable security and error detection and that we have error detection mechanisms to preserve the information that we're sending over, critical information at a critical time window, temperature, voltage, every 100 milliseconds, right? And that you have provisions to preserve that information or to detect potential corruptions, right? That's the other thing. So we do have good coverage when it comes down to that. The one thing I want to mention is we also developed this software development kit for the protocol with functional safety in mind. So the software was developed per ISO 26262 compliance process for software development. So it has ASIL-D systematic capability. And so we will provide all the documentation needed to show customers how to do the decomposition analysis from a software point of view. So FEMA reports, functional safety manual, that will come up with that software development kit as well. On the body monitor chip, as I mentioned, it's an ASIL-D compliant. We provide functional safety manuals. We provide meta reports and functional safety feed rate for these parts. And on the wireless MCU, it's a quality managed device. But as I mentioned, we are going above and beyond by providing functional safety manual and also FEMA reports for customers to do the decomposition analysis and understand what kind of coverage they can have in their system. This is just a quick picture showing the findings and what it is that we work with TubeSuite as part of the functional safety concept. Again, you can download this on ti.com upon request. And then really, when it comes down to security, we have a lot of provisions and security enablers for addressing concerns when it comes down to security threats, right? So we have key exchange and refreshment infrastructure for the whole protocol. We have a unique pre-programmed device ID with serial ID per radio. So that way, there's no way that, you know, a malicious party can actually clone these IDs. We provide debug security at the JTAG interface, so you can lock it out to prevent people to get access to the contents of the memory. We also provide software IP protection with read-only protections for flash sectors only. Secure firmware update, so we have an infrastructure in our devices to provide over-the-air updates. And we have a fully independent hardware accelerator doing cryptographic computational algorithms such as AES-128, ECC, SHA-1, SHA-2, and also has a true random generator as well. And so all these features are leveraged in the wireless BMS protocol and the wireless BMS solution that we're putting out there. Now, as I mentioned, right, this is a very scalable solution that allows car manufacturers to go up and down in the size of the BMS that they can support. And so going up to 100 nodes, really fast latency, the best-in-class latency in the market, down to 2 milliseconds per node. So what that means is that every 2 milliseconds, we can report all the critical information coming from the body monitor chip, all the temperature measurements in the 16 channels, all the temperature measurements on the 8 NTCs that we can attach to our part, you know, all the hardware supervision, cell balancing information, all that stuff is reported within 2 milliseconds, which is really fast. As I mentioned, this protocol has been designed with body management systems in mind. It's time synchronized, and you know, you can measure all the data in a very synchronized fashion across the different nodes. So it comes with a timestamp and so on and so forth. So it's a protocol that has been designed for body management systems in place. This is a picture of the evaluation module that we have for wireless BMS. It has everything on it. So on the top side, you can see that we have the body monitor chip, the BQ79616. We have all the necessary hardware to interface body module here, cells, basically on the bottom connector. And then on the right-hand side, you can see that the bottom side of the board, and that's where we have the wireless MCU, the wireless SoC. And you can see that we have a patch antenna. It's a PCB antenna attached to the board. So it's a very cost-effective implementation, having the two chips on a single board. So as part of the ecosystem that comes with this board, we also provide software code examples for driving the body monitor chip and for passing all that information through the protocol. So it's part of the software development kit. We also provide code examples for the main node coordinator that is coordinating and configuring all the network. And then we offer also a GUI, as you can see on this picture, for the PC to be able to take a look to key performance parameters on the network. Things like throughput, real-time throughput at the network level, at the node level, latency at the node level, at the network level, packet error rate at the node level, at the network level. And so able to record all those key parameters in an Excel spreadsheet so customers can look at it and then look at the performance down the road. So we have a lot of things going on with this ecosystem. Like I said, not only providing that GUI, but also provide a sniffer to allow customers to look at the quality of the signals. What is the receiver signal strength index on those signals to measure how the propagation of these RF signals are happening inside the body enclosure. So a lot of tools that are helping our customers to design these systems now. So as I mentioned, right, we have a software development kit that is readily available now on ti.com upon request. You can download it. We have a beta version now available. We'll have a production-ready SDK available by the end of this month, just a few weeks away from releasing our production-ready software. We have EVMs available upon request on ti.com. And then we have samples available on the wireless chip, the CC2662. And then we have now material available, production material available on 79616. This device was released to production last December. And it's readily available for customers to buy now. This is a quick summary of what wireless BMS solution is. So again, the importance of why going wireless BMS, we know it helps our customers to increase range because you can reduce the overall weight by replacing cabling and some other harnesses needed to secure connections and interconnects. We know customers like to go with this option because it reduces time to market for reusing a platform that can scale up and down for different car lines. As I mentioned, it's also helping customers to have a scalable platform for different types of capacities of BMS systems for different types of products and cars that they're designing in vehicles, and then helping out to manage warranties at the dealership side, right, without having to ship the whole BMS system and just only sending the module instead of shipping the whole thing, right? And these can be performed at the dealership side. So again, best of network availability. This network has more than 5 nines of availability. That is important in connectivity, in the connectivity world, because really what the 9.999% mean is just the probability of successfully sending information across the network, right? And so in order to be considered a cable replacement type of solution, you have to be at least 5 nines of probability of successfully sending that those messages and that information across. Our solution goes beyond the 5 nines because we have a lot of provision and a lot of mechanisms in the protocol to be able to mitigate interference, being able to mitigate challenges related to the propagation of the RF signals. That helps to basically have the best-in-class performance. System-level functionality, as I said, we took very seriously. Functional safety. Power consumption is the other thing that we took very seriously. We have the lowest power solution out there. It's a very well-optimized solution for trying to preserve as much energy as possible in the body modules. And then also being able to provide a very scalable solution, right? So trying to support larger networks so customers can have as many modules as they need for 18-wheelers, pickup trucks, right, commercial vehicles, or as little as just 8 modules for a sedan, for example. So offering that scalability by reusing the Saxon platform across the board.
You still with us, Daniel?
Providing a more cost-effective, a more scalable solution to car manufacturers. So with that being said, that's all I have for today. Rich, opening the mic for questions. Please kick us off.
Well, thank you, Daniel. I lost your audio for just a couple of seconds right at the end. Do you think you could repeat that last slide?
Oh, yeah. Sorry about that. Something happened on my side here. Can you guys hear me now?
Yep, sure can.
Something happened. So yeah, these, which one? This one, right? So on
Yep,
this one,
that's the one.
So again, what I was saying is we're working really hard to provide best-in-class solutions in the electrification efforts of the industry, right? So we believe wireless BMS is one of those solutions that can make a difference and help our customers to develop faster system, cost-effective systems at a much lower cost by reducing the manufacturing cost, the guarantee claim cost, and logistics cost involved when it comes down to having smaller pieces that you can ship around. So that's why I believe that wireless BMS could be a quick one of those breakthrough technologies that can help the industry to make this more affordable and then also expand the performance of the BMS system.
Excellent. Okay. So now we are on to the fun part where we get to answer the questions from the audience. And we do have a bunch in there. As I said in the beginning, ask them now because this is your time to hear the answers from our expert. If we don't have a chance to answer your question, somebody from Texas Instruments will get back to you when we're done. Okay, Daniel, here we go. How do you prevent the wireless, which I guess the wireless signals of a car, to not interfere with the BMS of a car that's in close proximity?
Yeah, this is a great question. I'm guessing that your question is related to interference happening in the same band, which is 2.4 gigahertz. And so the way we do it is having different provisions like frequency hopping, channel hopping, network synchronization, listing our nodes pre-configured. So those provisions help a lot to mitigate potential interferences in the 2.4 gigahertz band. So interference like Wi-Fi, classic Bluetooth, BLE, which will be in the same node, in the same band, right? And then what happens if you have multiple cars parked to each other, right? With all these sources of noise happening at once. So we've done a lot of testing around those conditions, and so we've injected a lot of noise trying to break the RF link, and all these provisions that we have in the protocol really make a difference when it comes down to having a robust solution.
So are you saying you were not able to put a situation together where the interference caused a problem?
It creates a problem depending on, obviously the amount of radiation happening, but what we are doing is minimizing and mitigating those effects by having different provisions on the way we handle the data, right? So things at the protocol level, like a media access controller, like frequency hopping, channel hopping, synchronization of the network really make a difference and really help to mitigate these potential challenges.
Excellent. Okay. How does TI's battery management system solution perform? Not exactly what are we looking for a benchmark, you think, there?
So I gave a couple of benchmarks when it comes down to key performance parameters. So, going beyond 5 nines of network availability is obviously one of the things that we've done in noisy environment. We've done a lot of testing around that. We know we provide the best-in-class availability. When it comes down to packet error rate, we're actually performing at 10 to the minus 7, so it's a very low number. Again, the feedback we're gathering from the industry is that it's best in class. When it comes down to power consumption, we're in the 100 microamps type of average current consumption at sleep mode. So again, best in class. So those are some just key performance parameters that have resonated very well in me.
Fair enough. How does TI's BMS enable security? One of my favorite topics.
Yeah, security, as I mentioned, right, we do have a couple of provisions and security enablers in the solution. So having a unique ID, having a listing provision, right, to be able to form the network and create the network, having hardware accelerators on chip and using encrypted messages, using message integrity check techniques to be able to, make sure that the information is coming from a well-known source. So we have a lot of provisions and enablers that allow us to basically offer a good suite of tools that our customers can use to put together a solution.
Okay. Let me paraphrase this next question because I'm not exactly sure what they're asking, but I think what they're saying is, would you discuss the scalability of the BMS?
Say that again, Rich. What do you mean by
Sure.
discussing the scalability?
Yeah. Would you discuss the scalability of the offering? How do you deal with that scalability, and how scalable is it?
Great question. So there are two things on scalability. One is, being able to provide options to customers to scale up and down with the array of the cells that they have in their system, right? So let's say for example, for a 100-volt high voltage system, you may use a 96S configuration. So we offer cell monitors with different configurations, meaning different channel support. So BQ79616 supports 16 channels. We have a port for 14 channels. We have one for 12 channels. So that allows customers to mix and match. We also have devices that also provide, in addition to cell sensing, monitoring voltage and temperature, we also can monitor current at the array level, at the module level. So that's another thing that we can do in offering flexibility and scalability by having pin-to-pin compatibility and reusing the stacks and register configuration. So you offer software compatibility as well. So that's one thing, right? The other thing is having a very scalable network that allows to have multiple modules. So you can actually configure this network to have 8 modules. If you want to have a very small network with a very small array that only supports, let's say, 100 volts and a very small array of body monitors and chipset, or going all the way to systems that can support 1,000 volts, right? And having an array of cells that needs to go all the way to 1,000 volts. And then meaning that you have more modules, right? And so that means that you have to have a bigger network for those kind of 1,000-volt systems. And so having a solution that can go with a very small network, going down to 8 nodes, 4 nodes, all the way to 100 nodes if need be. And so that's how we offer scalability, and we enable scalability to our customers, because they can use the exact same software, reuse the exact same hardware solution. The only thing they do is add more or less nodes and body monitors and chips, and that's it.
Excellent. Okay. What does the customer get with the TUV SUD assessed functional safety concept?
Yeah, it's a great question. So as I mentioned, right, when you get the whole suite of the wireless BMS solution, you get obviously an EVM along with the ecosystem. So as part of the ecosystem, you get a GUI, you get a software development kit for the protocol, you get a way to do RF signal monitoring. In addition to that, you get a set of documents that comes with all these different elements of the solution. So for the hardware chips, in this case, the wireless MCU, you get functional safety manual, you get FEMA reports. For the body monitor chip, you get functional safety manual, you get FEMA reports, and then you get functional safety feed rate. In addition to that, as part of the functional safety documentation, we provide a report coming from TÜV explaining what the functional safety concept is for wireless, meaning that how all these elements together help customers to achieve ACLD coverage at the system level. And then looking at all the different element decomposition analysis and the probability of error for random failures and systematic failures. So all that documentation is available for customers. So that's basically what they get as part of the suite.
Excellent. Is this BMS generally for a new design, or is it also suitable for an upgrade to an existing system or an automobile in this case?
Great question. So we have customers looking at retrofitting existing designs and upgrade their wired communication platform with wireless. So it's possible. There are just some things and nuances that need to be figured out, especially on the housing of the packs and how's that going to look like, because now you have to take considerations when it comes down to the propagation of the RF signal.
Okay. Do you need different certifications for different countries depending on where your automobile will end up?
Yeah, great question. It's no different than 2.4 gigahertz certification process. So you have different governing bodies all around the world. In the U.S., we have FCC, right? You have ETSI. You have some others all around the world for different regions and countries. So it's not different for any other 2.4 gigahertz, kind of application. Now, what I would say is we're using the unlicensed 2.4 gigahertz band, and we are operating within the boundaries of that and using the exact same type of architecture and configuration how the band is being used.
Okay. Would this technology lead itself to being used on other applications? I'm thinking other transportation related applications like rail or even aerospace or something like that.
Yeah, great question. The bigger the better, actually. We've had customer approaching us for other vehicle applications, not only for delivery trucks or 18-wheelers, but also for ships and railroads, right? So locomotive applications, So there is a huge push in the industry to electrify all sorts of vehicles, right? And the bigger the battery management system becomes, the more evident becomes the challenge when it comes down to wiring and cabling and harnessing. So wireless BMS is one of those technologies that, as I said, can help out customers to enable these to the next level. Another application that we've seen is also on energy storage systems when you have big farms with different big battery management systems there interconnected. So again, there is a need there also to remove cabling and harnessing and making the system more modular so you can easily service one of those modules if it's defective or you want to replace it.
Okay. Is the BMS ISO 26262 ASIL certified?
The battery management chip is ACLD compliance per ISO 26262. The CC2662, which is a wireless MCU, it's not. It's only quality managed device. But as I said, we're going above and beyond, providing additional documentation that help customers to do the decomposition analysis. Now, the software for running the wireless BMS protocol has been developed using an ISO 26262 process that has been certified. And the software systematic compliance should be able to achieve up to ACLD, and we will provide documentation around that. We will provide a safety manual and FEMA reports for the software as well. Now, that information, as I said, if you look at the tube suit concept analysis that we put together, explain exactly how those elements working together are able to help customers to achieve ACLD coverage at the system level.
Okay. Let's see. Here's a hard one to answer, but I don't have to answer it, so I'll give it to you. Are you able to quantify the dollar difference between a cabled solution and a wired solution? And if not in dollars, then how about percentages?
Yeah, great question. It's not that straightforward because there are many factors that influence the cost analysis when it comes down to comparing wired versus wireless. So it's just not at the BOM level. So if you compare BOM level on the wire and the wireless, obviously wireless is a bit more expensive because it has more electronics going into it, right? Now, when you compare all the other factors that I mentioned, like warranty claims and the cost of that, the cost of logistics and transportation, the cost of serviceability, the cost of manufacturability and reducing manufacturability time of wire versus wireless, that's when the benefits start to compound on towards the wireless, because those are the challenges right now that exist for the wired.
Is there a fear factor that you have to get past for people to do this wirelessly, or are we beyond that?
There's always a adoption kind of challenge that you have when it comes down to disruptive technologies, right? But when you start to look at the performance, when it comes down in real cases, real scenarios, and the overall benefits, that's when you pass that line. So it's really around, having customers understanding that wired is not a perfect solution right now. It's the only thing available, and they have to live with the pain points. If they started to look into wireless and see the benefits, play with it, that's when they get convinced. That's when they pass that fear factor. That's when they see, yeah, this works for me. I see the benefits. I feel that it mitigates and removes the pain points that I have right now with wired.
Very good. I was hoping you were going to say that. Well, Daniel, we're out of time. You did an outstanding job. I'd like to remind the audience that all Open Systems Media webcasts are copyrighted and may not be recorded without prior permission. Again, a thank you to our sponsors of the Automotive Technologies Virtual Conference, that being IAR Systems, Texas Instruments, Corvo, AD-Link Technologies, and Imagination Technologies. Please come back later today at 4 o'clock Eastern Time when we talk about the V2X Spectrum Coexistence Challenges presented by Autonomous Vehicles. That'll be presented by Corvo. And as I also mentioned earlier, we have more than a dozen pre-recorded sessions that are covering ADAS, autonomous drive, electric vehicles and powertrain, in-vehicle infotainment, and safety and security. So thank you, Daniel. You did an awesome job. And thank you to the audience for attending, because we can't do these things without you, obviously. So have a great day, everyone.